Hello and welcome to our last video notes for Unit 1, 1.7 here, where we're going to talk about modeling some data with linear models. So new vocab, we have a phrase, least squares regression line, sometimes shortened to LSRL, predicted value, residual, and coefficient of determination R squared. Some things we're going to learn on the calculator. We're going to learn how to find a linear regression equation and how to find the coefficient of determination, R squared. Turns out it's actually the same maneuver, but I thought I'd put it both there just so that way you remember that this video went over those things. So to get us started here, let's just jump right into a context and start thinking about how you would model some data. So here's a scatter plot for the total minutes played versus total points scored for 13 NBA players in the 2016-2017, well, that says 10-17, 2017 season. And all I did was use my eyeballs to try to fit a line to this. I didn't use any sort of math, fancy math like the calculator is going to maybe be doing for us in a bit. All I did was simply go like, this seems about right. And what I got here was this equation. So I got that points with the little hat on it. Why do I have a little hat on that? Well, that right there is representing a predicted value. We put a little hat on that in our equation here because we want to sort of signify that, well, this equation isn't going to be giving me the exact value here. So I have here in my data somebody that looks like they played 100 minutes. Just because I plug in 100 minutes, does that mean I'm necessarily going to get exactly that? Oh, it looks like I will actually, because that kind of goes through that point. Anyways, it looks like I have somebody who had like 810-ish minutes or whatever. 809, there it is. Just because I plug in 809 minutes doesn't mean I'm going to get exactly that Y value. You can see that it won't be true because I can see my line is way above that point. So that's why I have the little hat is to sort of signify the model predicts this amount of points for this player. So this line is a model for the relationship between minutes played and points scored, okay? And as you can see, the model is not perfectly right. No model will ever be perfectly right. You just hope that it's as best as it can be. So when I tried to fit this, I was hoping it was, in fact, as best as it can be, but I know I probably didn't do this correctly. So one measure of sort of figuring out, well, how close is your model making predictions is to think about this thing called a residual. So a residual is the error for the prediction of the model. So the calculation, the formula for a residual is the actual Y value minus the predicted Y value. To showcase this, let's go ahead and take a look at one example here. So as I was talking about, 809 minutes. A player played for 809 minutes. They actually, according to the point I can see right here, actually scored 221 points. What's my model predict, though? Well, I can go ahead and toss that into my calculator because it says that we got 2.5 plus 0.38 times the number of minutes played. Which, by the way, you might have noticed I'm not using X and Y there. That is actually way more communicative about like what goes where if you put in the actual variable names, which is expected of you. Well, it says that I would have predicted that they scored 309.92 points. So what's my residual? Well, I'm going to go ahead and subtract actual minus predicted, and I get the value of negative 88.92. Well, what does that mean to me? If I get a residual that is negative 88.92, well, it tells me this. It tells me that the model overestimated by 88.92 points. Or another way to say that is that the point fell below the model by 88.92 points. So either one is totally okay to sort of think about here, but I like using this sort of phrasing here. The model overestimated by 88.92 points. So we have another row here for you to complete on your own. So take a moment to actually fill this out. You can see up here is the points they're talking about for that next row. So go ahead and fill in and estimate and, calculate and then interpret what that residual means. So as I said, I drew in a trend line using my eyeballs, and I was hoping that it was like a good fit. Obviously, I'd like it to be the best fit possible. And so we often sometimes even use the phrase line of best fit. Turns out there's a lot of different ways to find a line of best fit. The one we discuss in this class is one model using the least squares regression line model here. So this is the best model with one of the most, like the goal of the model here is to kind of come up with the most accurate overall predictions. Now here's the thing, with a line, there's really only two things you can sort of mess around with. You can change the slope of your line, and you can change the y-intercept. In fact, that's the sort of the form we'll be using as those things. These are called parameters. So we only have these two parameters we get to monkey around with until we sort of get, what we hope is the best. So we need to find values for these that result in the smallest overall error is the goal. So how do you know that you have the smallest overall error? Well, one way you can do it is you can think about the sum of the squares of your residuals. That is what this is saying here. RSS, residuals squared, sum squared. I don't know which S is which S, but that's sort of the idea. So you can sort of see here, right inside the parentheses, that is the formula for a residual. It is the actual minus the predicted. And then we square it. Why do we square it? Well, we talked about this a little bit with standard deviation, okay? It has its merits and importance, but also like visually, it kind of helps make sense of it all if we jump down here and think about, well, what is a residual and what does it mean to square it sort of, visually? So we grabbed a couple of examples earlier. We had this residual right here for the player at 809 minutes. And so that's the residual right there. Well, what is the square of that? It is literally just the square that is created up of all sides being equal there. And so you can see that that's a pretty large squared residual. Same with the other one that we tinkered around with. That one is also pretty big. I'm just eyeballing what looks like a square. These are definitely not squares, but you sort of get the idea. So those are some pretty big ones that could be like detrimental to my overall equation. I probably did not eyeball the least squares regression line. But some of my residuals are very tiny. We can sort of see that this one is just that big right there. And way down here, like 200 and something, that's a pretty decent residual. So the thing that kind of needs to happen is, well, I have these giant ones, but I have these tiny ones. Is there a way I can sort of adjust my slope or my y-intercept so that way it kind of minimizes these? I'm never going to get all of these squared residuals to be all zero, but is there some place to put this line where it's not getting any smaller, okay? And if you've taken calculus, you might start to see an in here where you can use some calculus to try to figure out what this equation would have to be. In fact, I think it's just some really wonky algebra. You don't even really need calculus. But guess what? We don't need to do that at all. I have an error in here. I'm going to fix these before I go out on the video here. So it should be our values for A and B here, not M and B, because we're not calling them M and B in this class. We're calling them A and B. So what values of A and B would actually minimize all of this? Again, we are not looking to do this by hand, just like in our last video, calculating the correlation coefficient. We let the calculator do it. So let's see how that's done. So the last video that you watched, we actually did find a linear regression equation, but I wanted to just go over it again one more time. So if you feel you got it the first time around, fast forward. Otherwise, what you're doing is making sure that your data is in your lists. So this is the data for the number of minutes and points scored by those different players in the NBA. So make sure you have that entered. And then we're going to go to Stat, arrow over to Calc. And remember, we're using number 8, that form of the linear equation. My stuff is in list 1 and list 2 appropriately here. And a quick reminder, if you wanted to store your equation, because maybe you're going to make some predictions, or it actually will do something really cool that I'll show you here in a moment that will be very valuable to us next semester. Remember, to store it, you would hit the vars button right here, and then yvars, function, and then I'm just going to store it in the first one there. So go ahead and hit calculate, and there's all of my info. We have here A and B, got your y-intercept and your slope, and r squared, which is coming up in just a moment in the video, and r right there. Now, the really cool thing that we're going to really use, and that we've just talked about, is that when you do this linear regression, actually, it will also calculate all your residuals for you. So you can find those residuals in your lists. And actually, you don't want to go here. Here will not have your residuals. There's actually, if you see the stat button we usually hit has list up there, and you can hit second stat, and it actually now gives you the names of all of your different lists. Anytime you run a linear regression, it calculates and stores all of your residuals here in this list called resid. So that'll be something that we end up looking at a lot. Right now, it's not very important to us because we're calculating just individual residuals. We don't need to see all of them, but it will be something we use a lot in the second semester. So I thought I would point it out to you before the second semester, just to see what it's all about. So we came up with this equation here. We're using the a plus bx form, and so I'm writing it in that form here, where a is the y-intercept and b is your slope. So here's my equation, except not, okay? This is actually not going to get you full credit. Do you know why? Can you think why? If you want to pause before I reveal the answer, you can, but this is not correct. The reason it's not correct is because we don't use x and y. Those are not how we name our variables in this course. We use the names of the variables, and we have to signify that the response variable is just a prediction from this model and not the actual y values, the actual, in this case, point values that are coordinated with the different minutes played. So we would write instead, our y variable represents points. We'll put a hat on it because it's a predicted value. Our numbers are cool. We were okay with those numbers there, but we were not okay with the variables. And I always write the explanatory variable in parentheses. It's not important if you do or not. So there you go. That is a particular equation written out that deserves full credit. So keep that in mind, just as we've always been thinking about, context is of the utmost importance. And so if you just write y and x, context is gone. The other thing that the calculator spit out at us was r, so I'll go ahead and write that down. And it gave us the r squared as well. And that's actually what we'll be sort of continuing our conversation with on the backside. Now, before we move to the backside, I have a little note here. There's a little applet you can play around with if you're interested in this idea of sort of like wiggling around an equation or a line until you find something that you think is like the best fit. This little link here will take you there that you can sort of tinker around with to maybe sort of give you a more conceptual understanding of what exactly we mean by least squares regression line. So moving on to the backside here, we're going to talk about the coefficient of determination r squared. That is the square of our r values sort of, which I'll get into a little bit later here. So just in general, R squared tells you the predicting power of your model, okay? And it's always going to be a value between 0 and 1, because it is taking your R, which could be between -1 and 1, and squaring it. So if it was negative, then when you square it, it becomes positive. And so in this case, the closer you are to 1, sort of we're dealing with something that's a bit stronger. Closer to 0 means a bit of a weaker association. But there's a bit more to it. There's a way to actually sort of interpret what's going on here, and it has to do with variability, okay? So in any scatter plot, there's going to be variability, changes in your explanatory variable when there's variability in your response variable. So the x's change and the y's change, and they're, more or less changing with each other in some sort of overall fashion, okay? So the way we interpret an R value, I'm going to talk about it really out of context right now, and then we'll bring it back into context. So the R value states that blank percent of the variability, and variability is just a fancy word for like difference in, change in, of, oh boy, the Y can be explained by the variability of the X. That's sort of the sentence frame here. So the percentage is actually sort of your R squared value converted into a percent. And then it's talking about how any sort of change you're seeing in your Y values can be explained, this percent of the time, by a change in your X values, okay? So to really sort of make this make sense to us, let's look at an example where we're going to compare two pizza places, okay? We've got Pizza Time Pizzeria, and there, a cheese pizza that's large costs $12, and then it's $1 for every topping, okay? So if I went over to Pizza Time Pizzeria, sat outside, and customers came out, and I asked them, all right, how many toppings did you get? What was the cost of your pizza? Over and over and over again. I do this 50 times, okay? So here is the scatter plot that arrives from that, okay? As we can see, it is perfectly positive in terms of its correlation. So its R squared value, unsurprisingly, would mean it is 1. Its R squared value is 1. Again, this wouldn't happen in the real world usually. I set this up on purpose for this exact reason. So what does that mean in context? Well, let's write it down first and then talk about what it means. So using that sentence frame up above, what this means is, so 1 as a percent would be 100% of the variability in my Y values, which would be pizza cost, can be explained by the variability in pizza toppings, in number of toppings. All right, so what does that mean? That means that if I posed the following question, so if I bought a pizza from this place and you bought a pizza from this place, and I looked at it and I went, your pizza cost $3 more than mine. I wonder what would explain that. There isn't any question about it. Your $3 more pizza is only $3 more because you have 3 more toppings than me, okay? So if I was here and I looked over at you, I was like, I paid $13. And you were like, oh, cool. I paid $16 instead. Oh, what would explain that difference there between these? Well, there's only one thing that could explain that, which is you got 3 more toppings than me. 100% of the difference in our pizza costs is explained by how many toppings we got. There's nothing else that could explain that. All right. So that's an interpretation here for like 100%. Let's look at another example, though, down below. Platinum Pizza, okay? They have the same starting price, $12. but they have some different toppings. They got your standard, your pepperoni, your olive. Okay, those are $1 each. But they got some deluxe ones. Okay, you know, if you want like some blue claw crab on top, all right, that's $2 for that. Some interesting cranberries you want to put on there. Okay, if people are putting pineapple on pizza, why not cranberries? Those are going to be $2 each. So I did the same thing. I stood outside of Platinum Pizza. People came out. I said, all right, what is your cost of your pizza? They tell me. I said, how many toppings did you get? I did not ask them what types. I just said, how many toppings? And I jotted this down, and 50 different customers came out. I got all this data. Here's the scatter plot that's associated with that. So unlike with Platinum Pizza, which we could clearly see was a perfectly positive relationship, here, while I still have a positive relationship, it's a little less perfect. There's a little more variability going on here between all of this stuff. Okay, so crunch the numbers. Turns out R squared here is 0.79. So let's interpret what that means really quickly. I think you can do it, so I'm going to leave it to you. Then let's discuss what it means. So you should have said, and make sure that you actually write it down here. I put a purple star to remind you to write in your explanation, but you should have said something along the lines of 79% of the variability in pizza cost can be explained by the variability in number of toppings. So we're going to break down what that really means. 79%, where's this sort of number coming from? Why is that sort of making sense? So let's think about a similar situation here. So before I said, hey, I bought a $13 pizza, you bought a $16 pizza, what would explain the difference in those prices, right? So let's say that that's the case in our example. So I bought a $13 pizza, okay? So that means I bought this pizza right here. And you bought a $16 pizza, all right? So that means you bought this pizza right here, okay? So let's look at sort of the number of toppings we got, all right? So the number of toppings I got was 1, and the number of toppings you got was 4. Okay. So what would the model, though, predict? So you got 3 more toppings than me, just like before. But what does the model predict as the difference in our number of toppings? Well, for a person that orders 1 topping, my model seems to be predicting that I would pay maybe like $13.50, okay? And your model, or sorry, your example here, 4 toppings, the model predicts that you should be paying $18, okay? So the model predicts for us this difference here that I'm going to call, since it's like I'm saying about $13.50, I'm going to say is about a $4.50 difference here. So that's what the model says should be the difference. What's the real difference, though? Okay, well, the real difference, as we just discussed here, switch over to green, the real difference is here. Yours costs $16 and mine costs $13. That's actually a difference of $3. Okay, so the model predicted a difference of $4.50. The real difference in our cost, though, was $3. So did the model predict it perfectly? No. Did it predict it sort of okay? Yeah, it did. I would say a $4.50 difference is not crazy different from $3. It's not super off. Now, of course, sometimes it is super off. We'll talk about that. But this is sort of the idea behind the 79% is like, all right, if I have this difference in toppings, the model predicts this difference in our cost, but then there's the actual difference in those costs. And so how does it sort of compare? How much did it actually go like, oh, yeah, I almost got that. Like I nailed that one, because some of these, it is kind of nailing really, really well. But then there's other ones where it's not doing well at all. Like here, I'll give you an example here. Somebody bought this pizza right here, 5 toppings, $22. And then somebody bought 7 toppings for $20. Check out that variability there. That is not explained at all by the model. The model has everything positively sort of associated to here, but we can see that that's actually a negative change in our pizza cost. The model is not predicting that at all. So that's the sort of thing that kind of takes away from having a much stronger sort of R squared value, closer to 1, is these sorts of things that happen. If everything kind of increased together nicely, you get much, much stronger R value, but little things like this is what takes away. But my example with you of the $3 difference in our pizzas, that's actually something that did pretty well on there. So it's kind of thinking about all these different little ideas of like, okay, if I change the number, okay, different number of toppings, all right, what does the model say would be the difference in cost, and what was the actual difference in cost? How well did it explain that very observation over and over and over again, and kind of coming up with sort of this percentage of time that it explains these differences working together. So that's the main idea. You don't need to know any of that I just told you right there for tests, but I feel like it adds a greater understanding to the sentence frame. Ultimately, you can get by using this sentence frame up above and usually just be just fine for all our tests, MCQ, FRQ on the AP test. But I think there is an urge to like want to know, well, what does something like that even mean? And I hope this juxtaposition of pizza costs has helped explain a bit more. If not, please make sure you come in for flex time and let's talk more through this. So the next question usually is like, well, hold on, so 79% is explained by, that means there's 21% left over. What's that? Is it just gone and dust in the wind? No. The other 20% is in the residuals. The rest of it is in the residuals there. So, you know, the model predicts one thing and the actual value is off by a bit. So, like that difference, well, what could account for why the model didn't nail it? Why is it that it's not perfect? You know, it was perfect for pizza time. Why not platinum pizza? What else could be going on? Well, the residuals occur when your model isn't perfect because other things are happening. The other things that are happening are things called lurking variables, like, in this case, topping type. So the reason my model is off by that amount is because, oh, that's right, there's two different types of toppings. That's a third variable involved that now explains why I'm off by the way I'm off. So I set up this example so that we have exactly why we're missing it. But in most real-life examples, when we're dealing with scatter plots, there's not just one other lurking variable. There are dozens, thousands sometimes. And so, you can't just pinpoint it and go like, oh, I was off because of this one other thing. It's usually, I was off because there's these 19 other things going on simultaneously that the scatter plot is not showing us. So anytime you're dealing with sort of this, like, oh, my R squared is not 100%, it's because there are other things going on that are affecting the associations we're seeing, and that's why we have residuals to tie it back to the front side. So you might have noticed we're using a capital R here, when before we were dealing with the correlation coefficient, it was a lowercase r. Why are we doing that? Well, it's mostly to cover our butts because we should be actually using a lowercase r for all the examples we've been seeing here, and most of the examples we see in class, lowercase r, it works just fine, so don't freak out too much about which one you should use. But the uppercase r kind of works a little bit differently because it has a definition for it that would work with non-linear things. So I have here this formula that sort of shows you how an R squared could be calculated for any type of model, not just linear. So RSS we talked about there, residual sum of squares. And then there's this thing called TSS, which is the total sum of squares. So if you look over here at the definition, so the residual sum of squares we talked about here. In here we have, that is the definition of residual as a formula. You've got your individual y values, the actuals, minus the predicted y values there. On the bottom, though, there, what you're seeing is actually more like what you saw in sort of the numerator of a z-score. What we have here is a centering back to zero. We are doing an observation minus the mean of all your y values there. So this formula sort of has you think about like, okay, I got my residual squared. Now what's actually the difference from this y value back to the average of all the y values? And if we square them, because again, we don't want an absolute value due to calculus reasons, sum it all up, then we get this r squared value. Just like with r, you never calculate an r squared by hand, so do not worry about this formula too much. I just wanted to show you where it came from, because you might see some other formulas that look a bit different, but this one is one that is universal for linear and nonlinear alike. And that brings me to, if you know your model is linear, you can call it a lowercase r squared. So just for this course, we will be doing that, and that's totally fine. Just wanted to make sure that you pointed it out and got you to see the formula, because it's always good to see it, even though we're not using it. It might pique your interest and allow you to sort of, maybe explore a bit more. All right, so to end, I'd like you to fill out this table that kind of summarizes the difference between r and r squared. So what is another name for them? What do they tell you in words, okay? And then what kind of values do you expect them to be? Think about that sort of thing here. And then if you get done with that and you're kind of interested more in correlations and r-squareds, there's this game called guessthecorrelation.com. It's a little like 8-bit video game where you gain lives and lose lives based off of, you stare at a scatter plot, you try to guess the r value, you hit enter and it tells you yay or nay. It's kind of fun. It has fun noises associated with it. I think it's kind of cool, and I think it lets you gain a stronger understanding of like, just what kind of r values look like what kinds of scatter plots, which I think is helpful. So make sure you fill in this table. Make sure you've also answered your interpretation of Platinum Pizza's r squared value, and we'll see you in class.